Discrete mathematics is a very important branch of mathematics. Now we start with unit number 2 of discrete mathematics, that is lattices and Boolean algebra. Now maximal and minimal element. In the poset A precedes B means this notation. Now if A precedes B but A not equal to B, then we say A strictly precedes B, because as it is a poset, it is a reflexive relation. So every element A is related to itself. It means A precedes A is always true. So whenever we are writing A precedes B, that B may be equal to A or it may be different that A. So if A precedes B and A is not equal to B, then in that case we say that A strictly precedes B. Now an element A in a poset is called maximal element if it does not strictly precede any element of A. That is, if B is in A and A precedes B, then that B must be equal to A. See what is maximal element. Maximal element in the sense it does not strictly precede any element of A. Strictly precede because A precedes itself, that is true by reflexivity. But if A is not strictly preceding any element of A, then it is maximal element. It means if there is some B in A such that A precedes B, then that B must not be different from A, but B must be A itself. Now, what is minimal element? An element A in a poset is called minimal element if there is no element in A which strictly precedes A. That means if B is an element of A which precedes A, then in that case B must be equal to A. Now see the remarks. A partially ordered set may have one or many maximal or minimal elements. So maximal element can be one or more than one also if it exists. In a Hash diagram of a poset, upward journey is strictly prohibited from maximal element and downward journey is strictly prohibited from any minimal element of poset. Because by definition of maximal element, A is maximal element if it does not strictly precede any element of A. So, from A, upward journey is not possible if it is maximal element. Similarly, if A is minimal element, it means there is no element in A which strictly precedes A. So, from A, downward journey is strictly prohibited. So, considering this remark, it is easy to find maximal and minimal elements of given poset. Now next is least element and greatest elements. Now A is a poset. An element A in A is called the least element of A if A precedes X for all X in A. So if there exists some element A in A such that A precedes all elements of that set, then A is called as the least element of that set. Now, what is greatest element? Again, that A is a poset, then an element A in A is called as the greatest element if X precedes A for all X in A. So, if all elements in that set A are preceding A, then in that case A is the greatest element. So, X precedes A for all X in A. In other words, A succeeds every element in A. Now we have seen four elements: maximal, minimal, least and greatest element. Now see the remarks. The least or greatest element may or may not exist for a poset. If it exists, then it is unique. So maximal or minimal element can be more than one also. But in case of least and greatest element, it is only one. Then, usually the greatest element is denoted by 1 and the smallest element is denoted by 0. So, it is just the notation. The greatest element of a poset, if it exists, is maximal element but not conversely. Means if it is a greatest element, then it is a maximal element. But if it is a maximal element, it does not mean it is a greatest element. Same way, the least element of a poset, if it exists, is minimal element. But if it is minimal element, not necessarily it is a least element. Again, A is a poset and B is a subset of A. An element G in A, if it exists, is said to be a greatest lower bound of B if G is a lower bound of B and it is greatest among all the lower bounds. It means that if G dash is also a lower bound of B, then G dash precedes G. Means every lower bound of B will precede that G. Such a lower bound G is called as the greatest lower bound of B. Now these definitions are quite difficult to understand. So to clear the concept of all these definitions, we will see some examples. Now here, consider the posets represented by the following hash diagrams. In each case, write maximal element, minimal element, least element and greatest element if it exists. Now see the first diagram. So in first diagram there are four elements A, B, C, D. It means it is a partial order relation on set A, B, C, D. Now what is maximal element? So from maximal element upward journey is not possible. Now from A upward journey is possible, from B is also upward journey possible, from C also upward journey is possible. But from D upward journey is not possible. It means D is not preceding any element and so D is the maximal element. Now what is minimal element? From minimal element downward journey is not possible. So from D downward journey is possible. So D is not a minimal element. Again from B, C downward journey is possible. So they are not minimal elements. But from A downward journey is not possible. It means there is no element which precedes A. So A is the minimal element. Now, how to find least and greatest element? Now, if you observe here, A precedes A precedes B, A precedes C, and A precedes D. So, A is the least element because A precedes all elements of that coset. Now, if you observe here, A precedes D by transitivity, A precedes C, and A precedes B. Then B precedes D, C precedes D and D precedes D. It means all elements are preceding D and so D is the greatest element by definition. Now in next diagram, the poset contains the element A, B, C, D, E, F. So this is the set on which the relation is defined. Now first see maximal, minimal elements. Now, maximal element means upward journey is not possible from that element. So here if you observe E and F, from E and F upward journey is not possible. So they are maximal elements. And minimal elements are the elements from which downward journey is not possible. So minimal elements are A and B. Now, there are two maximal and two minimal elements in this case. Now, can you observe any element such that all elements are preceding that element? Then it will be the greatest element. See here, A precedes C, A precedes D, A precedes E. So finally we get A precedes E. Then same way by transitivity B precedes E, C precedes E, D precedes E. So A, B, C, D are preceding E. But what about F? F is not preceding E. So E is not the greatest element. Same way F is not the greatest element. Now what can you say about the least element? Now here a precedes C, A precedes D, A precedes E, A precedes F, but A is not preceding B, so A is not the least element. Similarly, B is not the least element, and so there are no least as well as greatest elements. Now see the third part. Now from C upward journey is not possible, so C is the maximal element. Now from A and B downward journey is not there, so A and B both are minimal elements. Now find greatest and least elements. Now A precedes C, B precedes C and C precedes C by reflexivity. So A, B, C all are preceding C. So C is the greatest element. But what is the least element? Is there any element such that all elements are preceding that element? So here for A, see A precedes A, but A is not the least element because B is not preceding A. Same way B is also not the least element. So there is only greatest element C but not the least element. Now see the fourth. Here again the relation is defined on A, B, C. As from B and C, upward journey is not there. B and C both are maximal elements. From A, downward journey is not there. So A is the minimal element. Now as A precedes A precedes B and A precedes C, it is clear that A is the least element. But what is the greatest element in this case? See, B cannot be a greatest element because C is not preceding B. Same way, C is not the greatest element. So there is no greatest element, only least element. So in first diagram, A is least element, D is greatest element, A is minimal element, D is maximal element. Now in second figure, E, F are maximal elements, A, B are minimal elements, but there are no greatest and least elements. Now in third case, A, B are maximal elements, C is the A and B are minimal elements, C is the maximal element, C is the greatest element, but there are no least elements. And in fourth diagram, A is minimal, B and C are maximal, A is least element, but there is no greatest element. So these are actually four different cases. In one, both greatest and least elements are existing. In another, both are not existing. In third, only greatest element is there. And in fourth, only least element is there. So we have shown it as a table. So in each case, maximal, minimal elements are existing, but least greatest element may or may not exist. Now next example is D30. So it is set of all positive divisors of 30. It is a partially ordered set with respect to divisibility relation denoted by this symbol. Find all the lower bounds of 10, 15. Then determine the greatest lower bound of 10 and 15. Find all upper bounds of 10 and 15. Determine the least upper bound of 10 and 15. Then find greatest element of D30 and least element of D30. Now before solving all these questions, it is necessary to draw the hash diagram for D30. So considering the ordered pairs present in that relation, using the conventions, we draw the diagram. So this is the hash diagram of D30. Now observe the diagram carefully. Now the first part is lower bounds of 10 and 15. So lower bounds of 10 and 15 are nothing but the elements A such that A precedes 10 and A precedes 15. Now here 5 precedes 10 and 5 precedes 15. Now is there any other element which precedes 10 and 15? Yes. 1 precedes 5, 5 precedes 10. So by transitivity 1 precedes 10, same way 1 precedes 5. So 1 and 5 are lower bounds of 10 and 15. Here 2 is preceding 10 but not 15. 3 is preceding 15 but not 10. So 2 and 3 are not lower bounds. So the only lower bounds of 10 and 15 are 1 and 5. Now among these lower bounds, 1 precedes 5 and 5 precedes 5. So 5 is the greatest lower bound. Now next is upper bounds of 10 and 15. Now for 10 and 15, upper bound is nothing but the L such that 10 precedes L and 15 precedes L. Now here 10 precedes 30 and 15 precedes 30. So 30 is an upper bound, but no such element other exists, and so 30 is the only upper bound of 10 and 15. So if it is the only upper bound, then least upper bound is that element itself. So least upper bound is again 30. Now greatest element and least element. Now by observation it is clear that all elements are preceding 30, and so 30 is the greatest element. Now as 1 precedes all elements in that set, because 1 divides all elements, 1 is the least element.